Hello everyone, this is Uddalak Sarkar. Today I will be presenting our work on the testing of horn samplers. This is a joint work with Professor Angshuman Banerjee, Shayak Chakraborty, Professor Saurabh Chakraborty, Professor Kuldeep Mil and Shantanu Sen. So first, what is a sampler? A sampler is just a randomized algorithm which, given a set as an input and a weight function as an input, samples some element from the set according to the given weight function. And a CNF sampler is just another sampler which, given a CNF formula phi as an input and a weight function w as an input, samples some satisfying assignment of the CNF formula phi and also generates a distribution over all possible satisfying assignment r phi. But the problem is the CNF samplers uses SAT solvers inside it, and this SAT solver heavily uses heuristics, and that's why it has no theoretical guarantees whether this distribution D generated by the CNF sampler will actually follow the input weight function W. So that's why the testers come into the picture to test whether the output distribution D actually follows the input distribution W. Testing of CNF samplers has been widely studied in a series of articles which developed this tool called Barbaric. But the problem with Barbaric is the Barbaric is not generic enough, and when the time comes to provide testing frameworks for some particular subclasses of CNF like the horn clauses or horn formulas, the Barbaric completely fails. The Barbaric does not work for horn samplers. First we define what is a horn formula. To define horn formula, first to define horn clause. A horn clause is a disjunction of literals with at most one positive literal, and a horn formula is a conjunction of these horn clauses. As you can see here, in this formula is a horn formula. It's because it has two clauses which are horn clauses, and these two clauses had at most or exactly one positive literal. There are two interesting facts about horn formulas. That is, the horn set can be solved in linear time even though the counting problem is in Sharpe complete. Testing of samplers falls into the domain of this distribution testing, and then there is this theorem by Panizki which states that testing whether the distribution is epsilon close to a uniform distribution has sample complexity of at least square root the size of domain in the normal sampling model, and this size of the domain can be of exponential order in the number of the variables of the formula. And as you can see that it is impractical to provide a testing frameworks using only this sampling model because that will require some exponential number of samples. But then there comes this conditional sampling model which was developed by Chakraborty et al. And Kannan et al. In conditional sampling model, along with the normal sampling axis, you can also choose a subset of the domain and query samples from only that subset of the domain. As you can see in this picture, on the right hand side of the slide, there is a normal distribution, and we know that the normal distribution when queried will only provide you samples within the vicinity of the mean. But in the conditional sampling model, you can use conditioning. You can just fix the subset which is on the left hand side of this vertical line and query the sampler to provide samples only from the left hand side of the vertical line. This is the power of the conditional sampling, and it has been shown that identity to a known distribution can be tested in order of 1 by epsilon square in conditional sampling model, which is just independent of the size of the domain. That's why the testers like Barbaric and our tester uses this conditional sampling model inside it. But the main problem or the main technical challenge is how to come up with this conditioning model. To do this, Barbaric designs this methodology called kernel, which, given a formula and two satisfying assignment of the formula sigma and sigma 2, comes up with a new formula phi hat, such that this phi hat has only two satisfying assignment, that is the sigma 1 and sigma 2. How does this help? Before, this phi with the CNF sampler comes up with a distribution D on the R phi, which is now when we feed phi hat on the same CNF sampler, it generates the new distribution D conditioned on S which is the sigma and sigma 2, on the new support set, which is only the sigma and sigma 2. As you can see in the images, the kernel actually does the conditioning on sigma and sigma 2. But then what is the problem of testing horn samplers using Barbaric? The main problem is this kernel completely fails, because the kernel, the new formula generated by kernel may not be a horn formula. Then, because the horn sampler doesn't understand anything apart from a horn formula, so that's a problem. Hence, Barbaric's implementation of cont is not consistent with the horn samplers, and that's why Barbaric cannot test a horn sampler. So then there comes our sampler tester Flash, which given a black box horn sampler G, a horn formula phi, a weight function W, Flash takes order of tilt cube by eta minus epsilon to the power 4 many samples, where eta and epsilon are the farness and the closeness parameters respectively, and with high probability Flash accepts the sampler horn sampler G if the horn sampler G is epsilon close to W, or the Flash will reject the horn sampler G if the horn sampler is eta far from W. And there, by tilt we denote the maximum ratio between any two satisfying assignments of phi with respect to W. So we designed a conditioning process which is horn consistent. That is, the formula that is generated by this encoding scheme called horn kernel is a horn formula. But there lies a small problem. That is, when we try to come up with a conditioning set, where the conditioning set consists only two satisfying assignments, that is sigma and sigma 2, we actually end up with a conditioning set having three satisfying assignments, that is sigma 1, sigma 2 and 0 tilde, where 0 tilde is a satisfying assignment with ones only at those places where both sigma and sigma 2 are 1, and all the other places it is 0. We call this assignment adversarial assignment because we did not want this assignment to be inside our conditioning set, but also we cannot block this satisfying assignment using only the horn clauses or the horn formulas. So we can't do anything. Rather, we will take care of this adversarial assignment in the decision procedure. During the decision procedure, what Flash does is Flash produces the samples from the phi hat using this horn sampler, and what it first checks is whether the number of the 0 tilde in the output samples is far huge than the weight of the 0 tilde. If it is very huge, then the tester immediately rejects the samplers. Thus we take care of thus at the first place we take care of the adversarial assignment. After that, if it is still not the case that the number of 0 tilde is very huge, then the tester will test the bias of sigma 1 and sigma 2. If the bias of the sigma and sigma 2, the bias ratio of the sigma and sigma 2 is far huge than the weight ratio of sigma and sigma 2, the tester immediately rejects the sampler. If this is also not the case, then the tester accepts the sampler. For our evaluation purposes, we use these benchmarks which are the horn formulas which has been used as a reliability computation of power transmission networks in US cities. And the samplers that we tested are the famous state-of-the-art samplers that are Unigen, Quick Sampler and STS. As you can see from the diagram that the number of samples queried by the Flash are at most of order 10 to the power 5, where the number of satisfying assignments of phi is growing for 10 to the power 32 to 10 to the power 143 for all the benchmarks. So you can see that the number of samples queried by Flash is actually independent of the number of satisfying assignments. This is the power of the Flash. Also you can see that Unigen, which has sound theoretical guarantees, is being accepted for all the cases. That is why it is taking so many samples, where for most of the cases quick samplers and STS, which doesn't have any sound theoretical guarantees, are being rejected by Flash. To conclude, we have seen that Barbaric does not work for horn samplers. As it is not a very generic kind of tester, it mostly works for CNF samplers. Then there comes our testing framework Flash, which is a very first horn sampler tester with sound theoretical guarantees. Some problems like linear extension sampling, which can be modeled using horn formulas, can also be tested using Flash. And designing testers like for the other subclasses like two-sat, dual horn, even Zor CNF can be a new direction to this research. As you have seen, like barbaric is not a very generic kind of tester. Coming up with testers which are more generic, or more general, can work for more subclasses or more things or more structures will be a future work or new direction or good direction to work on. Thank you.